everyone, in today's video we're going to be talking about section 8.2, the equals relation and equations. And you'll see that I have a balance, and we'll pretend that it looks like it's straight across. I know it's a little wonky, but it's balanced because what we're going to be talking about is the meaning of equality. So what is the equals relation? So this is our equals sign, and that asserts that two quantities or expressions are the same or represent the same quantities. Right? In the case of an expression, they may look different, but they represent the same quantities. So we're going to first formally go through the properties of equality. Properties of equality. And there are 7 of them. So 1, 2, 3, 4, 5, 6, 7. And whenever we're thinking about equality, I want us to think of this pan balance. This balance where we have two things, one thing on one side and one on the other. And if they're equal, that pan will balance. If they're unequal, one of them will go higher than the other. And so I'm going to put this transparency, and I know there's a little bit of a glare. I'm trying to block it. But there will be a little bit of a glare, unfortunately, because of where the lights are in my office. So the first property, and maybe this seems rather obvious, something is equal to itself. So in this case, A is equal to A. And this is called the reflexive property. A is equal to itself. So equality is reflexive. Something equals itself. But if we were to talk about, say, greater than isn't reflexive, right? Because 3 isn't greater than 3. And so you're like, well, surely, of course, A equals A. But this is a property of equality as opposed to another relation, right? And so this is the equals relation. There are other relations, greater than, less than, and things like that, for which that won't hold. Now another property that we have is that if some A equals some B, we have the opposite is true. B is equal to A. So I can read my pan balance left to right, A equals B, or right to left, B equals A. And this is called symmetry, symmetric property. If A equals B, then B equals A. And again, you might be like, well, of course, if A equals B, B equals A. That's true for equality. If we had greater than, if A is greater than B, then B isn't greater than A, right? And so symmetry is a property of equality. And now I'm going to draw a second pan balance, because I'm going to need it for the next couple. So if A equals B and B equals some C, oh, that C is really hard to read because it's in green. I'm going to use blue again, I suppose. If A equals B and B equals C, then A equals C. And this is called the transitive property. Transitive property. If A equals B and B equals C, then A equals C. Now I can't use greater than as an example of intransitive, and actually here I found another color. I'll use black for C. That way it looks different. Greater than is transitive. If A is greater than B and B is greater than C, A is greater than C. So I can't use my go-to counterexample. I'll challenge you to think of an example of a relation that isn't transitive. 4, we have suppose we know that A equals B, right? A equals B. Then if we add a C to both sides, A plus C does in fact equal B plus C. And this is called the addition property. Addition property. If A equals B, then A plus C is the same as B plus C. And where we have addition, we often have multiplication. So again, suppose A equals B. Well, if I have some number of those A's, say we have 5 of them, well, that's the same as having 5 B's. And that is the multiplication property. Multiplication. That's if A equals B, then C groups of A is the same as C groups of B. Right, and I've said C groups of A because I had that many A's and that many B's. This specific example is 5A equals 5B, but more generally, CA equals CB. And now, if we can add something and get their equal, or multiply both sides by the same amount and get it, we should be able to undo that because addition has an inverse subtraction and multiplication has an inverse division. So suppose I have A and B, and to both of them I had a C. So if A plus C equals B plus C, then get rid of the same amount from both sides of the balance, it'll stay the same, A equals B. So this is called the cancellation of addition. And so here we went, if A equals B, then A plus C equals B plus C. But if A plus C equals B plus C, then A equals B. We can undo that addition. And similarly, if we have some CAs and some CBs, we can undo multiplication. So we'll call that cancellation of multiplication. That's if CA equals CB, then A equals B. So another example of where this isn't true, for greater than, if you have -2 times, say, -1, and -2 times 4, I have 2 is greater than 8, -8, but I can't divide both and retain that greater than, right? It becomes a less than when I divide. And so while, again, a lot of these properties seem obviously true for equality, there are relations for which they don't hold. And it's important that we are comfortable with knowing these 7 properties of equality. Because particularly as we get into algebraic thinking, these are the things that we can do to both sides of an equation, both sides of the pan balance, and not disturb our equality. So we have, oh, I said there were 7 principles. There's one more, but it's so special it gets its own page. We call this the zero product principle. If A times B equals 0, then A equals 0, B equals 0, or both. For example, if we, and we haven't done polynomials in this class, suppose you had some polynomial x squared, or maybe a quadratic specifically, x squared minus I apparently can't quite think of one off the top of my head. So I need 2 things that multiply that add to give me something in the middle. So 2 things that multiply to give me 4 to give me, there we go. So suppose we have this quadratic and we said solve. Again, this is just an aside because I'll assume you've seen something like this before. Maybe not recently, but before. We can factor this into x minus 4, x minus 1 equals 0. And when we were solving these for the solutions, we then would say, well, x minus 4 equals 0, x minus 1 equals 0, and x equals 4 or x equals 1. So if I put 4 up here, I get 16 minus 20 plus 4, which is 0, or 1 minus 5 plus 4, which is also 0. So those are my 2 solutions. From this step to this step, and you may have never been told this, but to go from x minus 4 times x minus 1 equals 0 to this step, you're using the zero product principle. And so in my algebra and pre-calculus classes, I'm always very particular about saying we're using the ZPP, because I'm too lazy to say zero product principle every time. We use the ZPP from here to here. And this, again, is a property of equality. If A times B equals 0, then one, the other, or both of them must be 0. All right. Now let's do some examples. So I front-loaded a lot of these ideas about properties of equality, but what do we actually do with them? So I'm going to give you a set of 3 pan balances. So let me draw my pan balances. Those all look pretty even. And now I'm going to say, I'm going to use different colors so it's easier to see. There's a triangle. There's a triangle here. No triangle on the last one. And then I have a square, and a square, and a square. Triangle, square, circle, circle, triangle, square, square, circle, circle. And in each case, they're balanced by the number 12. This is balanced by the number 18. And this is balanced by 10. The question reads, what are the values of our triangle, our square, and our circle? So our triangle, our square, and then our circle. Well, let's think through this. And I used this example to start because if you remember from our last video, I had that farmer's market example, right? Where we were buying things and it was like, well, how much is it? This is exactly how we start to think about multi-step systems of equations and things like that. So it says, what are the values of triangle, square, and circle? Well, we know that square and two circles is 10. Well, there's a square and two circles. And by our cancellation of addition property, I know that this tells us that now let me write another balance. If I cancel my circle and my square, I'm left with a triangle. Make sure I use the right color. Triangle equals 18 minus 10. And so triangle equals 8. Triangle equals 8. Well, if triangle equals 8, and 8 plus square is 12, what do we know square has to be? Well, square has to be 4. Because we know that, I'll write this way, so 8 plus square equals 12, so square equals 4. And then if we use that, we can either use the fact that both of these, triangle and square, are 8 plus 4 or 12, or we can use the fact that this is 4 to get that 2 circles, so it can bring either from here or here, 2 circles equals 6, and circle equals 3. So circle equals 3. And we can confirm, so we have 8 plus 4 equals 12, good. 3 plus 6 plus 8 is 14, plus 4 is 18, good. 4 plus 3 is 7, plus 3 is 10, good. So those are our values of triangle, square, and circle. And you won't do these very long when you're teaching this in your future classrooms. But we'll use that as a scaffold when we talk about, say, solve 5x plus 1 equals 2x plus 1 with a pan balance and equations. So we'll go ahead and divide our page in half. We have our pan balance, 5x plus 1, 2x plus 1. Well, I know from my property, my cancellation of addition, that tells us the same as a pan balance that has 5x is equal to 2x. And I can take the same from both sides and not change it. So that gives me that 3x equals 0. And so this is my cancellation of addition. And then I used cancellation of addition again. I'll make sure. And then cancellation of addition again. And then 3x equals 0 by our zero product principle. 3 equals 0 or x equals 0. Well, does 3 equal 0? No. X does. X equals 0. And so then 5x plus 1 equals 2x plus 1. We can subtract 1 from both sides. 5x equals 2x. It's our first cancellation of addition. I can subtract the same from both sides. 3x equals 0. And then by the ZPP, x equals 0. Right, so you can see how using my pan balance together with my equations really helps us to reinforce what is happening at each step. But drawing pan balances is tedious, I'll agree. So we have the bar diagram at our disposal. So solve 3x minus 11 equals 13 with the bar diagram. So we have 3x. And from that, I'm going to subtract 11, and what we're left with is 13. Well, so that means that 3x is really 13 plus 11, or 24. So 3x equals 24. And that means if I were to divide that 24 into 3 equal pieces, x is equal to 8. Another one, solve 2x plus 5 equals 13 with a bar diagram. So I have my 2x, 2x, and then 5 more. This whole piece is 13. Well, if this whole piece is 13 and this part is 5, what do we know the 2x has to be? This piece, 5 and 8 give us 13. So we know that 2x equals 8, right? And that's what we would get if we would subtract a 5 from both sides. Divide by 2, x equals 4. Right, and this step here is the same as if I would add 11 to both sides. And so the important thing I want you to remember from this video is that we have our pan balance, we have our bar diagram, and we have 8 properties of equality. The zero product principle that says if two things multiply to 0, one or both of them are 0. And reflexive, symmetric, transitive, the addition property, the multiplication property, and then both of their cancellations. That's it for this video. Have a great day, everybody.